Welcome all. In this lecture, we are going to deal with example number 1. So, what does it says? A second order control system has a unity feedback and an open loop transfer function that is given as g of s equals to 500 over s into s plus 15. And what we need to do is we need to draw a block diagram for the closed loop system. Since we have a basic representation of the block diagram of a closed loop system as this type, this is our g of s, this is our input signal, this is our output signal, and if it is having a feedback system, since it is a closed loop control system, that's why it will have a feedback loop which is defined as an h of s, and it will go here. So carrying on this basic representation, we have to draw a closed loop system similar to this diagram, having g of s value is equals to 500 over s into s plus 15, and since it is a unity feedback, that's why h of s will be equals to 1 only. So the basic block diagram representation will be similar to this above diagram. So the input R of s is applied to this system and we get an output as c of s. Since here the g of s value is given as 500 over s into s plus 15, and since it is a unity feedback system, that's why h of s value is 1 only. So if we neglect it and modify this system, then it will look like this. This is R of s, which is input to this system. It is connected to the positive, and since it is a negative feedback, that's why we write minus sign here, and here we copied this term, that is 500 over s plus 15, and c of s will be acting as an output of our system. So this is all about the block diagram representation of a closed loop system. Moving on to the next part, that is write down the characteristic equation of a closed loop control system. Since the open loop control system that is defined as g of s is given as 500 over s plus 15, and we know that the characteristic equation can be determined as one plus g of s into h of s is equals to 0. So here the open loop transfer function is given like that, and also it is a unity feedback control system, that's why h of s is equals to 1 only. So putting the value of g of s and h of s in this expression, we get 1 plus 500 over s plus 15 into h of s value is 1 equals to 0. On taking the LCM, we get s square plus 15s plus 500 equals to 0. So this is nothing but a characteristic equation. Moving on to the next question, that is, what is the numerical value of natural frequency, that is defined as omega n, and the damping ratio, that is del. Since we know that the expression for the second order control system is given as C of s over R of s is equals to omega n to the power 2 over s square plus 2 del omega n s plus omega n to the power 2. So this is nothing but characteristic equation, and we also determined this characteristic equation. So on comparing both the characteristic equation, we can get that the omega n square value is equals to 500. Therefore, omega n to the power 2 will be equals to 500. This implies that omega n will be equals to nothing but under the root 500. It means that omega n equals to 10 under the root 5 radian per second. This is the value of omega n. We also need to find out damping ratio. So we have to compare this thing, that is 2 del omega n s will be equals to nothing but 15s. So we can also write it 2 del omega n s is equals to 15s. On cutting s with this s, we get 2 del omega n will be equals to nothing but 15 only, and we know that the value of omega n is nothing but 10 under the root 5. So on substituting, we get 2 del multiplied with 10 under the root 5 will be equals to 15. So this implies that the value of del will be 15 divided by 2 multiplied with 10 root 5. So on evaluating, we get del equals to 0.15 root 5. So this is the damping ratio. Moving on to the next step, that is sketch the transient response of unity step input. So we need to plot a transient response curve. So the transient response curve have the 4 conditions based on the value of damping ratio. Since we have recently calculated the value of damping ratio del, that is equals to 0.15 under the root 5. This is the value of damping ratio, and since the del is less than 1, that's why we can say that our system is underdamped system. And in the previous video, we have also plotted the time response for the underdamped system, and its time response will be something like this. This is C of t, this is t, and its time response will be like this. This is the peak overshoot value, that is denoted by maximum overshoot, and the time required in reaching the peak overshoot value is this time, and it is denoted by T of P. Moving on to the next question, that is find the value of percentage maximum overshoot, that is percentage MP, and the time from the start of the transient to the maximum overshoot, that is T of P. So we need to determine percentage MP and T of P. So firstly we will determine TP. Since TP is nothing but a peak time, is given as pi by omega d, and since we know that omega d is nothing but omega n under the root 1 minus del square, so replacing the omega d in this expression with omega n under the root 1 minus del square, we get Tp equals to pi over omega n under the root 1 minus del square. Since we have also calculated the value of omega n equals to tan root 5 and the value of del equals to 0.15 root 5. So substituting the values in the expression, we get T of P will be equals to pi value is nothing but 3.14 and omega n value is tan under the root 5 multiplied with under the root 1 minus square of this 0.15 root 5. So the value of Tp will become 3.14 divided by tan into 2.2360 multiplied with 0.9420. So on multiplying, we get the final value of Tp as 0.1491 seconds. So this is the value of Tp, that is peak time. Since we also need to find out maximum overshoot, and the formula for the maximum overshoot is equals to e to the power minus del pi over under the root 1 minus del square into 100%. So percentage MP will be equals to e to the power minus, since del value is equals to nothing but 0.15 root 5 and pi value is 3.14 divided by under the root 1 minus del value is 0.15 under the root 5 का whole square into 100%. So on evaluating, we get the value of percentage MP, that is maximum overshoot, equals to 32.69%. So this is the value of maximum overshoot. Moving on to the next step, that is settling time. So the settling time T of S is equals to 4 over del omega n. So T of S will be equals to 4 over the value of del is nothing but 0.15 under the root 5 and the value of omega n is equals to tan root 5. So here T of S is nothing but equals to 0.5 0.33 seconds. Moving on to the next question, that is, if the system is subjected to ramp input of 0.5 radian, then what will be the steady state error, that is denoted by E of SS. Since we are applying the ramp input of 0.5 radian, that's why we can say that our input signal R of t will be equals to t multiplied with 0.5. On taking the Laplace transform, it will be equals to R of S equals to 0.5, and the Laplace transform of t will be equals to s square. And since we want to find out the steady state error, that is E of SS, then the steady state of error E of SS is nothing but equals to limit s tends to 0 s into E of S. This is the formula for calculation of steady state error. But for this calculation we have to first find out E of S. The expression for calculating E of S is equals to R of S over 1 plus G of S into H of S. In the question we have the value of G of S and H of S. So on putting the values, R of S is 0.5 over S square divided by 1 plus G of S value is given in the question, that is 500 over S plus 15. Since it is a unity feedback system, that's why H of S is equals to 1 only. It is E of S. On taking the LCM in the denominator, E of S will become 0.5 over S square divided by S into S plus 15 plus 500 divided by S into S plus 15. So E of S can also be written as E of S equals to S plus 15 over S plus 15 plus 500, and on doing the cross multiplication of numerator, so 0.5 over S square. So this S will be cancelled out with this S square, and the remaining term will be E of S equals to 0.5 S plus 15 divided by S plus 15 plus 500. Since we have to calculate E of SS, which is given like that, that is limit S tends to 0 S into E of S. Limit S tends to 0 S into E of S value is this, that is 0.5 S plus 15 divided by S into S plus 15 plus 500. Here we forget this S, so this is also in the multiplication here, so this is also in the multiplication. This S will be cancelled out with this outer S, and E of SS will now become limit s tends to 0, 0.5 s plus 15 over s into s plus 15 plus 500. Since we know that s is tending to 0, that's why this term will become 0 and 0.5 will be multiplied with 15 only in the numerator. So 0.5 into 15, and in the denominator, since s is tending to 0 and s is in the multiplication with this term, that's why it will become 0 and the remaining term is only 500 in the denominator. So E of SS will become, after calculation, 0.015 radian per second. This is the final value of E of SS. Thank you.